Hey folks, how y'all doing? Um, Before we get started, just want to remind you that exam 3 is this Saturday. Let me turn that off. Which is the April 17th. Today is the last material that will be on the exam, which means that Wednesday and Friday this week will both be review sessions. Okay. And want to, if you're scheduled for a Monday class, but you'd rather attend a review session later in the week, you're invited to do so. All right, let's go ahead and get started. So, a couple of definitions here. If we have a connected planar graph, which is drawn so that in a way that no edges intersect, we say that a face is a contiguous region that's bounded by edges. Um, we also consider the unbounded exterior region of G to also be a face. So if I have a graph here, and none of the edges cross, then we count each of these as faces, but we also count the outside as a face also. Excuse me. Um, so this example has three faces because the outside always counts as a face as well. The plane in which the graph lies is separated into three different regions. One region inside the triangle, one region inside the other triangle, and then the leftover region that's outside both of the triangles. All of these are faces. We have a formula for planar graphs. Um, Let V, E, and F denote the number of vertices, edges, and faces. Then vertices minus edges plus faces always equals 2. Um, so in this example, vertices is equal to 1, 2, 3, 4. Edges is equal to 1, 2, 3, 4, 5. There are 5 edges. And there are 3 faces. And vertices minus edges plus faces is 4 minus 5 plus 3. 4 minus 5 is -1. -1 plus 3 is 2. And so the formula works at least for this graph, but in fact, it works for all planar graphs. That's kind of surprising that no matter how complicated your graph is, these always works out to be a constant. So base step, easy graph, easy step. If we have a connected planar graph with 0 edges, then it has to look like this. It's just a dot. And so there's one vertex, no edges, and one face. The entire region is just a one face. And so 1 minus 0 plus 1 does equal 2. And so that's our base step. We can do induction from that. So let's look at the inductive step. Let's assume that for all planar graphs with k edges, this works, and let's let G be a planar graph with k plus 1 edges. We're going to look at two cases. Let's suppose G is not a tree. Then G has a cycle. Let E be an edge on the cycle. Um, then G minus E is connected, but it has K edges. because we've deleted one of the k+1 edges. And so vertices minus edges plus faces is equal to 2 in the graph G minus E. So what happens when we put E back? Because E was an edge in a cycle, so E was an edge in a cycle, E made a face that was closed. And when we deleted the edge, this face and this face merged together. And so when I put the edge back in, I'm gaining an edge, but I'm also creating a separate face. I'm separating this one big face back into two faces. And so in G, E goes up by 1, and F goes up by 1. And so vertices minus edges plus 1 plus faces plus 1. Well, the minus 1 and the plus 1 cancel out, and we still get 2. And so if G is not a tree, then we can delete an edge from a cycle and then use induction to get what we want. If case 2, G is a tree, then there's only one face. Then G has a leaf node. Let E be the edge connected to that leaf node. Okay. Well, then G minus E is connected and has k vertices. It has k edges. And so V minus E plus F is equal to 2 in the graph G minus E. But in G, E goes up by 1 when we put the edge back, and the node at the end of that edge also comes back. And so, and V goes up by 1. Well, that means that we have one more vertex and one more edge, but the same number of faces. And the plus 1 and the minus 1 cancel, and we still get 2. So that finishes the proof for Euler's formula, V minus E plus F always equals 2. Okay, so let's start with another definition here. The side length of a face is the number of times that we have to count an edge if we're tracing the boundary of F. That seems pretty easy. For a normal shape like a triangle, that would be the side length is equal to 3. For a square, the side length is equal to 4. But let me show you an example here. What if my face has an extra edge in it? So this has a side length of 4, but this has a side length of 6. That if I'm tracing around the shape, 1, 2, 3, 4, I have to go up the edge and back down the edge to get through the cycle here. And therefore, I had to trace this edge twice. And so that makes this have a side length of 6. We're going to use side length in the next proof here. if we have a connected planar graph, so one of the things we know about planar graphs is vertices minus edges plus faces is equal to 2. Here's the next thing we're going to prove. Edges is always less than or equal to 3v minus 6. So let's look at a direct proof of this. We're not going to prove this by induction. We're just going to prove it directly. If we add up all of the side lengths, we get 2 times the number of edges, because we're counting every edge on both sides of each. We're counting every edge on both sides when we count all the side lengths. So the sum of all the side lengths is equal to 2 times the number of edges. No face can have a side length that's smaller than 3. That is, if we're going to have an interior, we have to have 3 edges. A single edge that we traverse once and twice doesn't have an interior to it. So no face can have a side length that's smaller than 3. And so 3 times the number of faces is less than or equal to the total of the side lengths. And so we have 3f is less than or equal to 2e. All right, so let's combine this inequality with Euler's formula. V minus e plus f is equal to 2. I'm going to multiply by 3 and get 3v minus 3e plus 3f is less than or equal to 6. And then I'm going to use the fact that 3f is less than 2e. And so I've got the inequality backwards here. I'm going to fix this in just a second. It says these things are equal, but 3f is smaller than 2e. Then this should be greater than. This is bigger than this. Sorry, I've messed up the signs in the proof, but I'll fix it up in a second. So these two are equal, but this one is larger. And so this has to be larger than or equal to 6. And therefore, negative 3e plus 2e is just negative e. And again, this is still greater than or equal to 6. And now here's where the sign changes. If I add plus e and minus 6 to both sides, then on the left side, I get 3v minus 6, and that's greater than or equal to. And on the right side, I get e. But that's the same thing as this down here. This line is correct, even though the signs in these other 2 lines were wrong. Okay? So e is less than or equal to 3v minus 6. All right, so that finishes up that proof. So now we know 2 facts about planar graphs. Vertices minus edges plus faces always is equal to 2. And then edges is always less than or equal to 3v minus 6. We're going to build another fact in just a moment, but let's go ahead and move on. If we have a connected planar graph, at least one vertex has to have degree 5 or less. So we can't have a planar graph where every vertex has a degree of 6, for example. Because if that did happen, then by Euler's handshaking lemma, that's the one where we add up all of the degrees, the sum of the degrees would be at least greater than or equal to 6v. But that's always equal to 2 times the number of edges. And that would then tell me if I have the edges is greater than or equal to 3v, because I divide this side by 2 and divide this side by 2. And that contradicts the fact that edges is less than or equal to 3v minus 6. And so this can't happen. This is a contradiction. And so we can't have every vertex have degree at least 6. One vertex will have a degree of 5 or less. All right. Well, this gets us to our kind of exciting theorem, I guess, if we want to talk about coloring problems. Um, if we have a planar graph, we have a vertex coloring with 5 or fewer colors. When I say vertex coloring, um, we're coloring every vertex and no adjacent vertices have the same color. Okay. So as an example, if I have this planar graph here, and I started coloring vertices, I can make this one red. But the vertices that are attached to it, they can't also be red. So this vertex could be blue. All right, but then this vertex could not be red or blue because it's adjacent to both of those. So we might make it green. There you go. This vertex here could not be green or red, but we could make it blue again. We could make this one red because it's adjacent to green and blue. But now let's look at this vertex here. This vertex is adjacent to blue and green and red, so it can't be any of those colors. We'd have to make it some other color like yellow. And so this graph, it took 4 different colors to color all the vertices. We have a theorem that says we can always do this in 5 colors or less. Okay? So let's look at the proof. Proof by induction, it suffices to show that every connected component has a vertex coloring with 5 or few colors or fewer. Because any disconnected part, we can just restart out the coloring process. So let's just say we have a connected graph. If H has 5 vertices or fewer, then we can just give each vertex its own color and we're done. So that's our base step. If H has 1 vertex or 2 vertices or 3 vertices or 4 vertices or 5 vertices, we just give every vertex its own color and we use 5 colors or less. So we're going to do induction on the number of vertices. We assume all planar graphs with k vertices have a vertex coloring with 5 or fewer colors. And we want to do a connected planar graph with k plus 1 vertices. Okay? So by a result that we already know, one of the vertices in H has degree 5 or less. So by the previous theorem, there is a vertex in H with degree 5 or less. Let's call it V. Okay. By induction, G minus V has k vertices. And so it's possible to color G minus V with 5 colors or fewer. Okay. All right. So I'm going to draw a picture before we move on to give you sort of an idea of what's happening here. Let's say I have this graph with this vertex V, and it has a degree of 5 or less. And then there's a bunch of other stuff going on out here. So these vertices are connected further out as well. But this vertex has a degree 5 or less. If I delete V from the graph, then by induction, I can color the rest of the graph with 5 colors or fewer. If the vertices that are adjacent to V don't use all 5 colors, say none of them use the color blue, then V could be blue, and then that would not contradict anything, so that we could give it its 5th color. So let me write out what that says. So if none of the neighbors of V let's say if, instead of saying none, if of the colors of 4 neighbors of V, 4 colors or fewer are used, then V can be the 5th color. And that solves the problem. The complicated example is what happens if V has neighbors and all of them have different colors. So let's say this one is red. I'll go ahead and use red and blue and green and yellow. Yellow is very hard for me to see here. Go. And something that might show up differently, maybe this purple color. So V is adjacent to already all 5 colors, which means I'm going to have to do something funny here. So let's call these colors C1 through C5 in some clockwise order. So doesn't matter where we begin, but we'll call green color 1, yellow will be color 2, purple will be color 3, red will be color 4, and blue will be color 5. Okay? And what we're going to do is we're going to look at the vertices that have our purple and green, C1 and C3. Okay? All right. So what we're going to do is we're going to take C1 and flip it from green to purple. But that might create a problem because C1 might have been adjacent to some other vertex, and that vertex was also purple, which means we'll have to turn that vertex from purple to green, and so on and so forth. So how do I want to say this? Let V be, no, not V, because I'm already using V. So let W be the vertex that's colored C3 and X be the vertex colored C1. Okay. I'm using 3 and 1 because I want to have a yellow vertex or some vertex in between them. Doesn't have to be yellow, but I don't want them to be side by side. Okay. Change the color of W to C1, and if necessary, adjust the colors of any neighbor of C1 of W, sorry, to C3, etc. So what we're going to do is, starting with C1, we're going to flip green to purple. And then if it had any purple neighbors, they flip the green. And if they had any green neighbors, they'd flip the purple. And if they had any purple neighbors, they'd flip the green, so on and so forth. All right. So everything works out fine unless this chain eventually connects back to C1 or C3, in which C3 flips to green. And then we still have 5 colors. Okay. If this chain includes the first color, okay, well, let's say first of all, what happens if this doesn't include X? If the chain doesn't include X, we will color the vertex V by which color? By the color C3. And we're done. Otherwise, so here's where things get tricky. And here's why I skipped one in between C1 and C3. We're going to try the same thing with C2 and C5. I'm sorry, C2 and C4. Actually, we could do C4 and C5, C2 and C5 also. Doesn't matter. But the one in the middle and one on the other side. I'm going to change this from yellow to red. And if it had any red neighbors, I'll turn them from red to yellow. And if they had any yellow neighbors, I'd turn them back to red, and so on and so forth. And this branch can't come back in contact with this one because the vertex where they intersect would have to be purple or green and red or yellow. And that can't happen. So otherwise, there you go. Change the color. The vertex at C2. So I should call this, go ahead and relabel W and X, but otherwise change the color of the vertex at C2 to C4 and adjust the colors of C2's neighbors. All right. If it C4 cannot get changed this way, since that would contradict C1 and C3 being. All right. So that's kind of the idea here, is that if I have 5 different colors, I want to create a blank a color that hasn't been used so that I can color this vertex by that color. So our first attempt to eliminate green by changing green to purple, and then going around and changing purple's neighbors back to green, and then green's neighbors to purple, and then purple's neighbors to green, and so on and so forth. And if this vertex over here remains purple, then I have eliminated green from the set of neighbors of this vertex. And then this vertex can turn green. Except for some reason I not seeing my pen. There you go. All right. But if there is a chain that goes all the way around from this vertex to this other vertex, now just repeat the process from vertex 2 to vertex 4, changing a yellow vertex to a red vertex, then make the next one yellow, make the next one red. That can't cross around and then that C4, because, well, that would be an intersection. And right there where they intersect, that vertex has to be either purple or green, and it would also have to be red or yellow. And it can't be both. So that finishes us up. Every connected planar graph satisfies this result and has a vertex with degree less than or equal to 5. Good. Y'all have a great couple of days. I'll see you next time.